about the how we're dealing with the vertical coordinate in MPAS, and at least some of the testing we've started to do in the model to see how it actually works. I'd like to start with a few sort of more introductory comments on the treatment of vertical coordinates in models. I think in most of the models that have been discussed over the last few weeks, there's the main things that are being used are either terrain following coordinates, where the coordinate surfaces follow the terrain, and then that influence of the terrain on the coordinate surfaces decreases with height until you get to the top of the domain. This has the benefit of being able to well represent smooth topography. It also makes it very easy to have selective higher resolution near the surface for representing boundary layer processes, things of this nature. The big drawback of the terrain following coordinate is the potential for numerical errors which can induce spurious circulations, particularly above steep terrain. And this is probably the biggest issue in computing the horizontal pressure gradient in the horizontal momentum equations, where one needs to compute this pressure gradient at constant z by taking a pressure gradient along the coordinate surface, which is sloped, and then correcting that back to this constant height by interpolating or extrapolating a vertical pressure gradient to get it back. This is also an issue, for example, in computing diffusion terms along, if you want diffusion terms along a constant height surface, that's a more complicated process as well. An alternative then is the cut cell approach, where the vertical or the coordinate surfaces remain horizontal. One can still represent the terrain accurately by appropriately taking into account the proper shape of these cells that are being cut by the intersections with the terrain. So this can work then for steep terrain as well as smoother, more gradual terrain. There are issues that require special numerical techniques in dealing with these cut cells. And from my own experience with playing with different cut cell approaches, this is one thing that I've continued to be somewhat uncomfortable about in terms of how we actually treat the numerics in those cut cells. I'll try to come back to that a little bit right at the end. And also, it's a little more complicated issue for resolving boundary layer processes, in that now since the coordinate surfaces are horizontal, if you have a stretched grid, you may have a lot coarser grid above high mountains than you do over low terrain. And so you need to have ways to deal with that. Now, Hiro Yamasaki showed some, what she's working on is embedding having higher resolution in the whole regions surrounding the mountains, which is one way to deal with that. What I'm going to be talking about for most of the talk here is terrain following vertical coordinates. And here, of course, we have the choice of having a pressure-based or a height-based coordinate. In a pressure, or usually it's hydrostatic pressure, this is the coordinate that we've used in the Whorf model that we've had a long time involvement with. And I would say that's the historical choice for global and regional hydrostatic models. Using a pressure-based coordinate allows the atmosphere to expand vertically, So if you have a constant pressure surface, if you're heating diabatically, the atmosphere can expand. If the mass in the column stays the same, the surface pressure does not go up. I think with current models that tend to have pretty high tops, this is probably not so much of an issue anymore. Another nice feature is the non-hydrostatic terms are readily isolated in one place in the code. And so one can easily put a switch in to just jump over those calculations. So you can have a hydrostatic switch to skip those calculations if you want the solutions just to be hydrostatic. So that's sort of a nice feature. We now have non-stationary coordinate surfaces as the heights of the pressure surfaces are changing with time. So we have time-dependent terrain metrics, if you like, or in other words, the way to say it is we now have additional time-varying variables. Now the geopotential or the height is changing, and so on. Also, if one wants to remove a reference sounding from the equations, this can certainly be done, but it is definitely more complicated, and for people not familiar with the details of the technique, it can be pretty confusing. Whereas with height-based coordinates, this has been the historical choice for non-hydrostatic and non-hydrostatic cloud and mesoscale models. It's typically employed with a rigid upper surface, although it doesn't have to be. And one nice thing is that since the height-based coordinate surfaces can remain fixed over time, we have a lot more flexibility in how we define those surfaces, because once we define them, they stay fixed, and we don't have to mess with them while the model's running. So we've made the decision to go with a height-based coordinate for MPAS. I don't know if I wrote it on here, but a height-based coordinate definitely provides somewhat simpler looking numerical codes, and our experience with WRF in supporting a modeling system to a large number of community users is that there's a lot of benefit in having a code that's simpler and easier to understand. We've had a lot of issues in our community support with the hydrostatic pressure coordinate, just trying to help people understand what it really means.
With respect to these two choices?
Well, other than the difference in the upper boundary condition, I'm not sure what you're thinking about. I mean, you can still have your whatever the spacing you want, the grid spacing can be whatever you want it to be in either one.
Well, basically delta p's are small, whereas delta z's must be large if you want to still cover like 100
Sure.
kilometers.
But that small delta p corresponds to a large delta z. So you've got that relationship between the pressure difference and the height difference either way, regardless of what your coordinate is. So we haven't seen any.
I was wondering if it numerically would make a difference.
Not that I'm aware of. With the pressure coordinate, you've got that external mode, and the deeper the atmosphere, the faster that mode tends to go. That can be dealt with in the pressure-based system.
Is it the same limitation for stability with respect to the slope of the mountain?
Yes, essentially.
More or less.
Yeah, those are essentially the same issues.
Hey, Joe, does your choice of terrain following or Z coordinate influence the coordinates, or are they completely? Are there 4 reasonable combinations?
No, you said the choice of
terrain following versus, you could have a cut cell, sorry, terrain following.
Versus cut cell.
You could do cut cell and Z or pressure, I suppose.
That's true, yes. You can do that either way.
So is there one that's more, are there combinations that you feel are poor choices?
No, I think whether you've got a pressure-based or a height-based system, the issues you face with the terrain following or cut cells are the same, except there is this difference that with the pressure-based system, the coordinate surfaces are moving in time, and so that gives you somewhat less flexibility in how you define those coordinate surfaces. I think that's the main thing. So in terms of different formulations for the terrain following coordinates, I'm now going to be talking just in height-based system. On the top line here is what I call the basic terrain following coordinate, where the height of coordinate surfaces zeta is defined such that it follows the terrain height h exactly at zeta equals 0 at the surface, and then the influence of that terrain drops off linearly with height until it just disappears totally at the very top of the model. And so you can see then that the influence of the terrain on the coordinate surfaces is present throughout the entire domain. Okay. A modification of that that goes back to Arakawa and Lamb and Simmons and Burridge is to just simply put a profile in front of this terrain height that instead of decreasing linearly with height, can decrease more rapidly than linearly. And there's a lot of arbitrariness to some extent in how rapidly you choose to remove that terrain influence. And so with the hybrid coordinate, then if you let this A be 1 minus zeta over zt, this A looks like this dashed line. If you make A equals 0, you get a pure height coordinate. And then you've got a lot of flexibility to make this drop off more rapidly than linear. And then, as you can see over here, what that means is when you get to a certain height, there is no terrain influence. You're back to constant height. So this is good. It removes terrain influences faster with height. So things like errors in horizontal pressure gradients and diffusion and so on at upper levels can be pretty much removed. With this approach, all terrain scales are removed at the same rate with height, because whatever this profile is, it multiplies the entire terrain shape. So small scale, large scale, everything goes at the same rate. Now, but we have to remember that down near the surface, there still is this issue with the computing pressure gradients along the contour surfaces, which again have to follow the terrain. Christoph Schaar and collaborators proposed a modification to the hybrid coordinate, which allows smaller scale structure to be attenuated more rapidly with height. And what they did was essentially modify the hybrid coordinate approach and basically split it into two pieces. So instead of just something times the mountain height, they made two profiles times two pieces of the terrain height. And this is done in a way such that, let's say that if this is the true terrain height h here, they define some smooth version of that terrain height, call it h1, and it's sort of arbitrary how you decide that smooth version should be defined. And then H2 is, of course, just the difference between H1 and H. It's whatever is left. And so then a traditional hybrid coordinate is applied to each of those two pieces, except now, as you can see over here, the attenuation profile is removing the influence of the smaller scale part, the H2, more rapidly with height than this smooth portion, which is attenuated more slowly. So it's broken into two pieces and damping the smaller one more rapidly. What we've tried to do is a little different than that, because the idea is basically that, well, we feel that the influence of small scale terrain structures on these coordinate surfaces ought to be, the smaller the scale, the more rapidly that influence on the terrain surfaces ought to be removed. And so we do it in a more continuous way. This again looks a lot like the regular hybrid coordinate formulation, except now instead of h, the terrain height here, we have a more general function, which is also a function of the coordinate height, as well as x and y. And basically the idea is, instead of having this hybrid attenuation factor acting on the terrain height at every level, we take this terrain height and start smoothing it as we move up in height. So imagine that we take the terrain height here, h. At the first coordinate surface, we run a Laplacian smoother over it. And we can run that a number of times if we like, till we get a somewhat smoother representation of this terrain. And then we use that somewhat smoother profile up here. And then we go up to the next coordinate level. We take whatever we had at the one below and smooth it a few more times, and then use that. And each time we move up one level, we use a smoother and smoother version of the terrain in the hybrid coordinate. So what you're looking at here is not what the coordinate surfaces look like. This is what this HS looks like. And then this attenuation factor, which might look something like this with height, is what multiplies each of these contours at different levels. And then the trick is, one thing, one has to be careful in smoothing. You can't smooth too much, or you can drive these coordinate surfaces into each other, or maybe even make them cross. So there's always a constraint that you don't want the minimum delta z to drop below some specified minimum. So let me give you an idea of how this works then. Here's a resting atmosphere simulation that we did using this Char-type mountain profile. And now instead of, in Christoph's paper, he used a 250-meter mountain. This is a 1-kilometer mountain. And we've specified a thermodynamic profile, a potential temperature profile, if you like, that has constant 0.01 stability up to 2 kilometers here. Then there's a 1 kilometer deep, essentially isothermal layer with n equal 0.02, and then it goes back to this lower lapse rate. The reason we put this structure in is that if you put a constant stability profile in for one of these experiments, the vertical pressure gradient is nearly linear. And if the pressure gradient is nearly linear, then you won't produce much error in making the correction to the computing horizontal pressure gradients along the contour surfaces and then adjusting them. So by having these sharp changes in stability, that puts more stress on computing the horizontal pressure gradient accurately. So I think it's important to, if you want to really see how things work, to get some structure into the atmospheric profile. So this is non-hydrostatic. We're down at a 500-meter horizontal and vertical grid here. And if we run out to 5 hours here, this is what the coordinate surfaces look like for, this is the basic terrain following coordinate. Now, remember, the top of our domain is up here at 20 kilometers, and I'm only plotting it up to 5 kilometers. So we're only seeing the lower quarter of the domain. So you see there's only a quarter of the terrain influence is removed here. This is the hybrid where it's being moved more aggressively so that the terrain height is essentially, or the terrain influence is essentially 0 by the time you get to 5. And this is the one that where it's got the hybrid but also smoothing the surfaces. And this one, the differences are sort of subtle because this is not real small scale when you compare these two. But if you look at what the potential temperature field looks like in this inversion, you can see that we've got significant distortions in the basic terrain following coordinate. They are significantly reduced with the hybrid coordinate and further reduced when we do that, when we do the smoothing.
But if you would move inversion lower with the smooth coordinates, would it be the same, or would you have an effect like above? Because inversion could be in at different places.
Yeah, it could be, and I would say it's we get a similar qualitative difference if you get the even if you bring it right. In fact, I have some experiments where we bring it down to mountaintop level, and you still see improvement. The differences with the basic terrain following, when you get it way down near the surface, get smaller because at the end of the day they all go to follow the terrain when you get down to the surface.
You haven't tried it with cut cell, have you at all? No.
Well, yeah, I have. Here's the cut cell result. There it is.
Right, okay. Oh, sorry, okay. That was actually...
It's
the same. What's the problem?
What?
What's the problem?
No.
Well,
Seems like we have the answer.
No, you don't.
Well, these resting atmosphere experiments can be deceptive. If I use a reference sounding in my model, which happens to be the same as the initial sounding, I'll get zero pressure gradient errors in the terrain following coordinate as well. So you have to be careful how you look at these. Here's another experiment that's a little more exotic, where we've actually taken the actual terrain in a cross-section across the eastern slope of the Rocky Mountains. So Boulder, Colorado sits right here. So there's a lot more smaller scale structure here. And again, this is the top of the model's at 20 kilometers. We're only looking up to 5. This is the basic terrain following hybrid, and then our smoothed hybrid. So here you can see that the terrain influence is being removed rapidly, but if you also do smoothing, you can see how the smaller scale structure is being selectively removed very quickly as you move, as you get above the terrain. And again, this has got an inversion that's actually intersecting the high parts of the terrain. And again, you can see that things get better as you go to hybrid, and better again as you go to the smooth version. This is a plot of the maximum vertical velocity in those three, with the basic terrain following, the hybrid, and the smooth. So the maximum vertical velocities is coming down.
What's the unit for W?
This is meters per second.
Meters per second.
Yeah, it's big.
Wow.
Do you have an analytic or quasi-analytic solution for that setup?
Yes. The analytic solution is U equals 0, W equals 0, theta prime equals 0.
Okay.
In other words, nothing happens.
So the blue line.
So we know the right answer.
To bring that. Okay.
Yeah, so all that, everything you see here that's smaller scale wiggles in this field are spurious circulations.
Did you do the same experiment with pressure as a hybrid coordinate? Like rather than
Yes.
Is it the same?
It's basically the same. Okay, so we want to put this in MPAS then and run it on the globe. So what I did then is to take our essentially our full MPAS model, and I'm running these on that little laptop, and so I'm just running with a coarse 120 kilometer nominal resolution. We're running 40 levels in the vertical with a stretched grid, so we have a small grid increment of less than 100 meters down at the surface, and then expanding upward to a top at 30 kilometers. We use the high resolution terrain data interpolated onto that grid and then run one pass of a fourth order terrain smoothing on that. And I've specified an isothermal reference sounding. And then, so the idea is that we initialize the model on the sphere. We have the real terrain. We specify a single sounding at every point on the terrain, and we specify 0 initial velocity. So we're sitting there with a calm atmosphere that's as a single sounding. And again, I've put in now the sounding, so it's got a constant lapse rate up to 6 kilometers, a 2 kilometer deep isothermal layer, and then constant lapse rate again up to like a tropopause at 12 kilometers, and then isothermal above. And the maximum terrain height sits just under this at 5,400 meters. What I've chosen to do here is just to show you what solutions look like after integrating for a period of 3 days. And I looked around to kind of find the place where things were the worst. And this cross-section at 30 degrees north that goes through the south side of the Tibetan Plateau is a pretty, seems to be about as interesting as it gets. This is what the coordinate surfaces look like with the basic terrain following coordinate above that cross-section with the basic terrain following, and then with our smooth coordinates here. And I've blown up this box over here so you can see a little better how the terrain influences are different. For example, here, even this little feature here, you can see, you can follow that all the way up. This is 12 kilometers here at the top, whereas you see how that's being removed more aggressively with height with the terrain smoothing approach. So now if we look in the same cross-section, here's that potential temperature field with that inversion between 6 and 8 and then above 12 kilometers. I'm only plotting these up to 18 kilometers so we can see more of what's going on down low. This is with the basic terrain following versus the smooth coordinate. And these are the perturbation values of potential temperature. So you can see there are significant perturbations developing even up here near and above the tropopause, whereas those pretty much disappear with the smooth coordinate. If we look at other fields, this is vertical velocity with the basic and the smooth coordinate. And this is essentially the absolute value of the horizontal velocity. This is square root of 2 times the horizontal kinetic energy. And again, you can see that significant perturbations that we see at upper levels are now pretty much removed with the smooth coordinate. I haven't said too much about how we're computing the horizontal pressure gradient. Everything I showed in those pictures is computing the horizontal pressure gradient in what I would say is sort of the traditional way, where we have a gradient along the coordinate surface, and then we adjust it with a vertical pressure gradient that takes into account the slope of the coordinate surfaces. This is written in a form that's d by dx and d by d zeta, so it's a nice conservative form sitting in the horizontal momentum equation. But you see this averaging that's needed to get vertical pressure gradients are essentially over 2 delta zeta, and they have to be interpolated to get to this, back to this velocity point with the C-grid staggering. There's another approach that really goes back to Maurer in '84, where the idea is instead of computing pressure gradients along the contour surface and adjusting it, you look in the vertical column to find the point that's at the same height as the velocity point, and then just interpolate the pressure directly to that point in this column on this side, and the column to the left over here, and then just take that difference straight as a dp dx at constant height.
How are you doing for material?
Yeah, it's getting close to the end here. So what we're doing here is what I call a simplified version, where we only allow that interpolation to move to be within a grid interval above or below, instead of looking for that point where it might be several grid intervals below. One can do this. Gunther Zengel talked about this last week. It's sort of the approach he's using. It requires more complicated bookkeeping of where all these points are, whereas if we just interpolate between the pressure at the same level and then the next one either below or above, depending on the slope, we just have a very simple calculation for these pressures. So it's very easy to include in the model. These pictures on the left are our basic terrain following and the smooth coordinate that I showed you before. This is what they look like when we use this, what I call modified pressure gradient. So it's getting smoother. This is what I showed you before again with the perturbation theta values, and this is with the modified horizontal pressure gradient. You can see again that the perturbations are noticeably reduced. And I think there's one left with the horizontal velocities are showing that similar improvement when we use this different formulation. I do have one simulation that I did on a full data, full physics, real data, full physics case. Here we don't really know, I haven't done any verification statistics to know what you really would like to have, but in this, it's a 4-day forecast from October 2010, and looking at a cross-section across the southern Andes where there was strong cross-mountain flow. You can see this is what the vertical velocity cross-section looks like in the basic terrain following coordinate and our smooth coordinate. To me, this looks more like what we would expect or want to see the wave structure look like above this terrain. But again, we don't have a quantitatively right answer. I think, whoops, because of the time, I'll skip my comments on the shaved cell. I got off the end. So anyway, we have decided to go with a height-based coordinate because of the flexibility, efficiency, and simplicity of the coordinate. Using the smooth coordinate allows us to remove the influence of smaller scale terrain features selectively more rapidly than the larger scale features. This is something we can't really do with pressure-based coordinates like we have in WRF, because those coordinate surfaces are not stationary in time. So there's several things that help mitigate these pressure gradient forces errors in MPAS. We have the smooth vertical coordinate, this modified Maurer scheme in computing the pressure gradients, And we're also expressing pressure and density as perturbations from a reference sounding, which helps make those terms somewhat smaller. So I'll stop there. Thank you.
Thank you. I'll take the opportunity to go first. Sorry. Which of the versions of the horizontal pressure gradient, if any, imply that the the total pressure gradient is curl-free? It is.
Well, I would think that. Oops. Expressing it in its upper form, I think you would have the ability to do that. If you chose.
If you actually want to curl free, you have to do the line integral, right? So he's basically doing two sides, but if you do the full line integral,
Yeah, so you've got to use these points as well to do the.
if you do the full line integral,
gradient.
you're guaranteed that every line integral is touched exactly twice with the opposite side.
Which is presumably, is that, are they pressure, yeah, we usually don't have a list.
Well, I think we're losing that feature when we do this interpolate, that what is modified Mars scheme.
Sarah Jane and then Rupert.
So I get the impression that one of the obstacles to using these more sophisticated vertical coordinates in an operational model is just the number of parameters that need fixing. And I wondered with your coordinate whether you'd looked at the potential improvement only from, so not doing any of the smoothing, but just using your different function for removing the terrain height with height, because that looks very different to the descriptions in the sleeve coordinate and the hybrid terrain following coordinates. I wondered whether you get a good improvement just from that A of zeta.
Yes, I would say you do get significant improvement by using just a basic hybrid coordinate over terrain following. And many models do a hybrid coordinate, like the CAM coordinate is a hybrid coordinate. So getting rid of that terrain influence by somewhere.
But I mean specifically with your cos to the 6 sort of form, does that have a big? I mean, it seems like a very different sort of removal of the terrain influence than the more exponential shape.
Well, this is something you can play with. I mean, some models use just a linear form. Shar used a hyperbolic sine, a cinch profile. There's no real magic to that. I think the idea is you have to be careful down here. You don't want to remove the terrain influence too fast right above the mountain, because you start to push those lower coordinate surfaces right down onto the top of the mountain. So the idea is to have gradual attenuation right above the mountain and then get more aggressive as you go up.
Before we take any more, does anyone have the, I'm thinking about timing. Rupert is giving a talk this morning and a talk this afternoon. Is there anything after your talk this afternoon? Because maybe we could switch both your talks to this afternoon. Has anyone got the programme of talks?
Oh, I see. I thought there was.
Has anyone got the web up on?
Yeah, I think there's only, right now there's only scheduled to be just his talk this afternoon.
That's
So-
correct, in a discussion.
But a discussion based on Rupert's talk, so it's your, so one option, depending if everyone's happy with it, and it's also going to involve Steve, who's recording everything, is that we could move your talk from this morning to this afternoon. Would people prefer that, or shall we press on now and hear from Rupert this morning?
Well, I think
It's up
that
to Rupert.
maybe must have, because we still have a lot more questions to Joe. If you want
So that's
to-
one vote for moving Rupert's talk to this afternoon. Any other?
What was that? What was the point for having it in the afternoon?
Move my talk, both
Got two
of my
talks.
talks to the afternoon and keep discussing now.
Let's turn this into a general discussion of vertical coordinates.
Right.
of that
Any
flavor.
objections to that? If Steve is listening at the back, will you be able to record Rupert's talk? Oh, you already? Thank you very much. It'll be a full hour this afternoon.
It's like the Wizard of Oz back there behind the screen.
Rupert's on it.
Yeah, I do. There's a huge number of papers, meanwhile, on web balancing of all sorts of source terms. And the idea, we have heard it in a talk earlier this week, is to get rid of the imbalances by discretizing the source term in the same way as you discretize the gradients and divergences of the fluxes. And then we did that in 2004 in a JCP paper for this kind of problem, and got the vertical velocities down to centimeters per second rather than meters per second this way. And we never worried much about the particularities of horizontal pressure gradients, because the major error was taken out by that strategy. Have you ever considered that, or do you have a comment on that?
Well, I guess I don't understand why that would remove the problem.
Well, because the major error that comes here is from the fact that you have the hydrostatic pressure gradient vertically, and your discretization is skewed to the direction of this beast. And then if you ask for clean horizontal pressure gradients, you have to find these balances. If, however, you have a reconstruction locally that says, I'm basically locally subtracting out the hydrostatic balance from what's going on, then that thing is gone. The only thing you have is truncation errors of the leftovers. And that seems to work extremely well.
Well, if you assume these are hydrostatic, for example, you can replace that the PD zeta term, just replace that by G rho, right? You can actually use the hydrostatic equation in there.
No, we didn't. What we used was that the pressure is nearly hydrostatic. So we constructed a discretization of the gravity term that looks like a pressure gradient by locally reconstructing a hydrostatic pressure gradient and taking that gradient and doing the same discretization on that beast that we do with the normal pressure. And that cancels the main errors from that.
But then you've got a hydrostatic pressure gradient where your pressure is defined in the center of the grid volumes.
Yeah.
And then you've got it at the next grid point.
Yeah.
And now, but those are done, I assume those are column constructions.
This is all local reconstructions. You don't have to connect them. Because you're only after the pressure, the gravity term, which is a totally local quantity, right? It's rho times g. So you do that evaluation locally.
Right.
The key point is you do it by locally reconstructing something that looks hydrostatic and discretizing that as a pressure gradient. And then what happens is the truncation errors from that discretization have the same structure as the truncation errors from your pressure gradient term. And then you don't have this weird interaction of truncation errors that produces the vertical velocities.
Well, I need to see that in more detail
yeah, right. Yeah. Okay.
To see what that means.
Todd and then Sean.
I think there's at least one limit where the smooth hybrid terrain following coordinate is the same as sleeve. So if you go to the previous slide, or at least I think it's the continuous, it's the end limit of sleeve. So sleeve is basically keeping the first term in sort of almost a wavelet expansion, right? It has a beam, then it keeps a coefficient times a delta, right? So the H2 is the delta. It's the difference between the H1 and the H2. Right. You can continue that on to infinity, right? As an expansion,
right?
Where we conceptually think of each expansion as higher wave number information. And each expansion gets a B.
If you
right?
So you're saying, well, you could Fourier decompose this and have one of those for each wave number, for example. Yeah.
And that's exactly what's on the next slide. Because if you go to the next slide, by doing this Laplacian smoothing, you are essentially providing a B
right.
for different wave numbers as you go vertically.
Right. So to me, the advantage is instead of putting everything into two bins, we're essentially separated into as many bins as we have wave numbers. And the highest wave numbers are being removed more rapidly.
Right. So I think by using a del squared smoothing, you've made a very precise or a very clear definition of what those B's are as a function of wave number.
Mm-hmm. Yeah, that's a good way to think about it. One thing I wanted to say that's kind of in the may help a more general discussion regarding cut cells and what happened to that thing? Well, there used to be a slide in there. I wonder if it had a designation of don't display or something.
Yeah, there, but you hided them. Number 19, maybe. 19, slide 19, Joe. Slide 19.
Yeah, 19 and 20 are black.
Just click.
19,
There it is. If I try to display that, it's going to, yeah. With this smooth coordinate, one can produce, for certain situations, the same coordinate surfaces as the cut cell. For example, as long as the height of the mountain is below the level of the first grid level, you can say, well, I'm going to smooth this thing, or if it's a hybrid coordinate, you can say, I'm going to attenuate this thing so fast that there's no terrain influenced by the first grid level. So every grid level, there's one more slide in here. And that's not going to come up either. It's interesting. I must have them as hidden slides. Okay, so as long as the mountain height's below the amplitude of the first grid level, I can smooth this thing. I can use my smoothed or hybrid coordinates to have exactly the same coordinate surfaces as the cut cell. And so I was looking at what that means just for a simple mountain wave simulation. And now if I try to go back to that next one, I'm going to lose it. Oh, no, there it is. Okay. So what happens if I actually use my code with the smooth coordinates for that case? I get a nice solution. This is perturbation potential temperature, and it looks pretty reasonable. In my cut cell code, where I assume that the pressures and thermodynamic variables are defined in the center of the uncut cells, that's where I start getting noise produced in these cells that are getting small. But when I compare these, it seems to me that this smooth coordinate approach in this limit is sort of telling us where these points really ought to be located, which is in the center of the uncut cell. And so if I take that cut cell code and I actually modify it to put the location in the center of the uncut cells, so now these points are located at the same point as these points, then I come back to getting nice solutions again. If you believe that, what that means is that at the lowest grid levels in the cut cell approach, you should not be taking pressure gradients at constant height. You're going to be taking them along surfaces that are, in some sense, terrain following. And so that's sort of a dilemma I've been scratching my head on in terms of can you really use a cut cell approach where you assume the horizontal coordinates for all the variables are constant height, even right next to the surface? I don't have an answer, but that's the question.
If you look at what is done, how cut cells are used in CFD applications, typically they are combined with a finite, they are finite volume formulation. So they are associated with values which are defined at the center of mass of the elements, which matches your figure on the right, not on the left.
Right, but then you end up computing pressure gradients not on constant height surfaces.
Yes.
And I think that's the goal of what a lot of these cut cell formulations are trying to do.
Jean, and then Frank, and then you. Yeah, Jean. Frank.
You see that you have a reference temperature. Is that dependent on X, Y, Z, or just D, or?
It's only dependent on Z for
And for global model, you don't.
for global model, it's more problematic as to, well, it's not problematic to impose it, but it's more problematic as to how much benefit it gives you, because yeah, expecting the real atmosphere to be close to that sounding is not going to work.
But does it have an influence on the stability or accuracy of the total speed? Is it just
It does not have an influence on stability. It will have some influence on accuracy in that kind of one of the motivations for having a reference profile is that you're now doing your pressure gradients on perturbation values, and so if those perturbations are small compared to the total value, then things like these pressure gradient errors are going to be smaller because we've removed the piece of that pressure gradient from the reference sounding, and so we're only worrying about the perturbations. And if those perturbations are large, then the potential errors in computing those gradients will be larger. Whereas if like in mesoscale in limited area models where we have a reference that may be reasonably close to the real atmosphere over most of the domain, then it's more beneficial.
So Joe, the cut cells, does that complicate the inclusion of physics because you have now non-constant number of points at each column?
I don't think that the number of points in the column varying is such a complication so much as you may not, depending on how you formulate it, you may not be getting consistently uniform or the resolution that you'd like near the surface, particularly for boundary layer processes. I know Jürgen has addressed this, Jürgen Steppler. He actually has a dual grid. In his cut cell model, he also has a train following model, and he interpolates his fields from the cut cell grid to the train following grid, does the physics on the train following grid, and then brings that back to the cut cell grid. So there's more complications, I think, in trying to get the physics applied sort of the way you'd like to with uniformly high resolution near the surface.
Firstly, I was wondering how many criterions when we design and we want to smooth the sigma levels, above the steep terrain. And in my mind, that seems like two, right? And first one is we don't want to see the surface levels intersect with each other. And the second thing is we want to get as smoother as possible, right? Mm-hmm. And so there's something like two sub-questions below this one. And first one is how to do. We don't make the sigma levels intersect. And the second one is, in all this method, I think we should calculate how fast this slope decay with the height, but I don't see that the results.
Well, unfortunately, there's no unique way to.
Actually, we can calculate that, right? Because we got the definition, and we can calculate slope and then calculate the lap rate, right? Because we got the definition. And so there's another question about this. If we
well, let me address a couple questions I pulled out of your first statements. There is this trade-off between how much smoothing we can do and keeping a reasonable vertical spacing in the coordinate. Because when we go up at every column, we want to have a reasonable progression of the vertical grid size, and we don't want the vertical grid increments to get too small. You can imagine, for example, at this first grid level, if you smooth too much, you would start to drive the height of that coordinate surface right through the terrain. Because if you keep smoothing this, it'll go right through there. And so you have to have some kind of criterion that you don't let the minimum spacing drop below a certain, say, fraction of what that spacing is in the undisturbed sounding. But there's no single way to do that. It's something that, I mean, what we do is we don't let it drop below half of what the spacing is in the sounding without terrain. But there's no magic to that. You could pick a different number if you like.
I see. And the second question, maybe like, if we use this, now the left figure, the profile, if we use this profile,
This one.
yeah, this one, and into the sleeve, and now to the H1 and H2, so the definition seems similar to this one, but I think there's difference, right? So what is the difference? If we
Well,
this profile to the H1, both H1 and H2.
Yeah, here I didn't say what this H1 and H, or this, here it's B1s and B. I didn't say what those were. What Char used is a cinch profile, hyperbolic sine that drops off. And what I showed on that other one was a sine to the 6th power. There's no unique way to specify that, and so you've got a lot of choices. The main thing I think in both of those profiles is they drop off significantly faster than linear, and they may have an upper level where they formally go to 0. But there's no magic to how you define that that attenuation.
My question is, in a broad sense, the vertical coordinates we are using in these models, they are non-inertial frames, right? Like the sigma or the surface pressure. Why are we not able to use an inertial frame?
I'm not sure what you mean by that.
I mean, like if you take the stand, like whatever you are trying to measure, a coordinate, it is an absolute. That means it's invariant. It is invariant and inertial. It doesn't change from place to place, right? Like we fix a frame on this coordinate axis as a height.
Mm-hmm.
Like it is fixed. So with respect to that, we can calibrate the thing and measure the scale. When we use a surface pressure, that is like that can vary with respect to the changes in the thermodynamics.
Mm-hmm.
That is one aspect. Second problem I see is that like the topography itself is a varying one. Can I have something independent of these two? That could, I think that will be at the, that could provide a direct way of measuring things.
Well, both of those approaches though are used in order to get the coordinate to conform to the actual terrain surface at the surface. Right? So you're sort of stuck with that. And then you've got a lot more flexibility of what you do as you get above the surface. Okay, and if you want to relax that, then you're going to have coordinate surfaces that are intersecting the terrain, which you can do, but then you're faced with approaches more like the cut cell approach. So at least from what I've seen, you've kind of got one of two ways to go.
Yes, right. Yes, to avoid having, to avoid the problem of not having lines that intersect. have you actually tried to apply the Laplacian at once on the entire domain? And also, wouldn't that decrease the number of iterations, the global number of iterations you would have to do to solve your Laplacian, instead of doing layer by layer? Because of the property of your Laplacian, they will never intersect, so you do it at once and you smooth out the entire domain.
Yeah, you could do it all at once everywhere. But what that would do is essentially give you the same amount of smoothing throughout the domain. And what we really want to do is to have to progressively smooth what originally was the true terrain. We want to smooth that more and more as we go up. So rather than thinking about this as a number of iterations, I mean, the way I think of it is we want to do a certain amount of additional smoothing to that contour as we move up to the next grid level. And the simplest way that I found to do it is just to run that simple horizontal Laplacian on it several times and then move up to the next one. But there's other things you could do as well to do that smoothing. It's just a matter of we want to have that smoothing be progressive with height, so that we're progressively removing more and more of the small scale structure as we move from one level to the next.
Because you always want to keep your boundary layer grid, stack of grid following the terrain.
Because at the end of the day, we have to, at the surface, we have to be using the actual terrain. And then we go up. Now, the nice thing about this, like I was talking about these MPAS simulations, it really doesn't take very long to set this grid, for the whole model. And the other thing that's nice is you only do it, it's part of the initialization. You just do it before you start running the model to set the grid, and once the grid's set, then you go. And don't mess with it anymore.
I just have a quick comment on the terrain point versus cut cell slide. Could you show me the secret slide?
The secret slide, yes. This was the secret slide, I think, right?
Yes. I think the question is really interesting, and it looks terrain point grid and variable height cut cell grid looks exactly the same. But
they are the same, yeah.
But the tricky thing is, in this case, the topography is only in the lowest level. But once you cut the cell in the second lowest or third lowest, it should look different. There should be a difference.
Oh yeah, because now if this comes up through this coordinate surface here, now this one will be pinched off, and now this coordinate surface will be starting to follow the terrain, and so its centers will be starting to go up. So this my terrain following smooth grid that I'm kind of using as a guide for what I should expect with the cut cell. That can only work as long as this height stays below that first coordinate surface. Yeah, I didn't mean to imply that this is I can just turn this on and run it as a replacement for cut cells. It'll go nuts if this goes through that first grid surface.
We've got 2 more comments, and then it's definitely time for coffee. Niels and Alan.
I have 2 comments, really sorry.
I used them all.
The one is that we have done this test in our model with respect to this zero flow. And we get also like sort of on the order of centimeters, despite the fact that we use a hybrid sort of A plus B times coordinate. And I'm wondering if it was because we calculate the horizontal gradients in spectral space both for the pressure on the one hand, for the local surface pressure, and for the orography on the other. So going to very high order, if you like. I wonder whether that sort of makes the difference.
Now, what kind of grid are you talking about? What kind of horizontal grid are you talking about?
The horizontal grid. You mean this is our classical Gaussian grid, basically?
No, but I mean, how large scale are you doing this experiment on?
Oh, on a small planet, like, you know, like yours, basically. So it's a very small spacing. Like, you know, when we model the shear mountain, so the grid resolves the shear mountain, basically. So we've put it on a small planet, basically.
And what did you use for your atmospheric sounding?
I can't remember, but I think, you know, Sylvie did this, but she looked at one of your slides from your presentation, an earlier presentation you gave. So I guess she was trying to, you know, replicate your run.
Well,
I don't know whether that's the reason why, you know, that would be the case.
Well, yeah, let me just say, I think one has to be very careful in comparing resting atmosphere experiments from one model to another, because there's so many things that can cause large differences. Obviously, what you use for your atmospheric sounding will make a big difference. Whether there's a reference profile that's been removed from the thermodynamic variables, and if so, what it is, will make a big difference. The amount of, if any, of dissipation in the model will make a huge difference. If you turn on, you know, like 10 meters square per second of viscosity versus none, it makes a huge difference. And so I'm very, very cautious about comparing totally different models without a lot of care, where I think the biggest value to me in a resting atmosphere experiment is to evaluate sensitivity within a single model. Because then whatever you got, it's going to be the same, and you can change one thing at a time to look at a different form of the coordinate, a different form of how you compute the pressure gradient, and get a more controlled difference. So I think we have to be very cautious about that.
My second comment was
and then I'm
whether
definitely coughing.
any of this will help, because the most challenging problem I have come across now is, in fact, when you go like to these very high resolution simulations, where Mount Everest and Lhotse become a very prominent peaks in the Himalaya, and prominence means the relative rise from the nearest mountain range, if you like, to the top is very high. And what happens is in winter, when the jet stream comes very low, it hits this mountain. And it actually, in our model, creates an instability in the sense that you create very large vertical velocities suddenly, and it just sort of goes back. Will any of this help to alleviate that meteorological situation that does occur? Because, I mean, the jet stream comes very low, it does hit this very prominent mountain with very high speed, and you know, it goes with very large vertical velocities, and our model cannot cope with this at the moment, I believe. I'm wondering if, you know.
Yeah, and there you're having a physical situation that's stressing the way the model is set up and run. I mean, for example, you could have a situation where you just need a smaller time step in order to stabilize those higher speed disturbances.
To a much smaller time step.
Well,
we'll just get by, but you know.
but yeah, I mean that's kind of a different issue, I think, than what we're talking about here. I don't think this is likely to solve those problems.
Okay.
Alan,
very quick one, and to comment on that. With 4-minute time steps, you're never going to solve that problem. I see it as a physical problem. But the question I've got here is that one of the challenges I see is when you have these gung-ho type grids. I mean, that looks all very pleasant. But when you've got 32 options of shaved cells in a sort of octagon or whatever you've got, was that done in MPAS? I would see that as a big challenge.
This was just done in my two-dimensional toy code.
So my comment was, have you thought about how you might do it in a sort of octagonal, pentagonal sort of thing, which I think is a great challenge that we need to look at.
That is certainly an additional complication. My approach has been that I wouldn't even start thinking about those issues unless I was comfortable with how it worked in the simplest application. I don't know, Hiro, do you want to comment on that in terms of how you see the complications of adapting the cut cell approach to the more complex horizontal grids like hexagons and so on?
Oh yeah, so I sometimes think about how to say hexagonal cell. I'm going to be slightly mad, so I'd like to stick to Cartesian grid at the moment. Not sure.
I mean, certainly in principle, you can apply your approaches to that, right?
The typical problem is I'm using a merging cell, so I don't.
Oh yeah.
What do you think about merge the hexagonal grids or?
Well, you can merge vertically, okay.
Vertically, yes.
Vertically you can do it, but yeah, horizontally you're screwed, I think.
We better leave it at that. Thank you very much, Joe. Everyone else.